In the next section, we're going to talk about improper integrals. So improper integrals are integrals that somehow involve infinity. So they're improper, right? They're not the normal definite integral where everything is finite, bounded, etc. An example of this is, let's take the function y equals 1 over x squared and look at the area under this curve from 1 on. So I'm going to take the area all the way out to x going to infinity, right? So that kind of is a strange concept to sort of think about that. The area then, what I want to do is I want to take the integral all the way out to infinity. Okay, but I can't write this, right? I mean, I wrote it, but I haven't defined what that means. That doesn't mean anything to us yet because we only defined integrals in terms of finite areas, right? But what I can do is I can define it for a finite area from 1 to, say, let's say instead of going all the way out like that, let's say I just want to go to here. That's t. And then maybe I want to go a little further, and I want to go a little bit further. So that's kind of what I can do. And in fact, the way we want to define what this means when there's infinity in one of the limits of the integral is we want to not consider that, which isn't defined, but we want to consider this, which is defined 1 to some number t. Then I do this integral, which I can do, because these are just numbers. And then once I'm finished with the integral, I'm going to take that limit as t goes to infinity. So when I write this down, I really mean this. Okay? And now this I can do, I ignore the limit, I just do the integral, I evaluate it at 1 in t, or whatever that lower limit happens to be, and then I take the limit. If the limit's finite, that's great. Then I have my answer. If the limit doesn't exist, that's also an answer. Right? So let's see what happens here. So this is an easy enough integral to evaluate. Right? This is going to be minus 1 over x. And then I'm going to evaluate from 1 to t. So make sure I have enough space here. This is going to be minus 1 over t plus 1. Okay, well now I can take the limit of this as t goes to infinity. This first part just goes to 0, right? So I get 1. So in fact, even though my area is going out infinitely, it has a finite number. So this integral, even though it has an infinity in it, I'm able to, once I write it like this, I'm able to get a finite number. I'm able to get a finite area. And that's because this goes down so fast that very quickly, I'm not adding very much more as I take that t further and further and further. Okay? So when the integral has a finite answer, we say the integral converges. Just like a limit, we said just like limit, right? So we'll say the integral converges, and it converges to 1. So you want to find out what it converges to as well. Now, mind you, of course, they don't always converge. A lot of them diverge. In fact, we can make a very small change here. We can consider the function 1 over x, which looks very similar, but doesn't go down quite as fast. So that's now my 1 over x. It's going down a little bit slower. It goes up here a little bit faster too, right? That's not a great picture, but you get the gist. So now if I do this, let's do the same thing. This integral is different, right? Because dx over x integrates to natural log. So I have the limit as t goes to infinity, natural log of t minus natural log of 1, I should have an absolute value. I have an absolute value here, but t is always positive. So this is always positive inside because I'm going out to infinity, so I can drop that absolute value. This one is 0, but this is the limit as t goes to infinity of natural log of t. Well, you know that's going to infinity. So here's an example. Looks very similar to the first, but it doesn't go down fast enough to give us a finite area. So this integral diverges. I don't have an answer. Well, that's my answer. My answer is that it diverges. I don't have a finite number. So that's how we're going to do these. By the way, this kind, when it's gotten infinity in the limits, these are called type 1. Okay. There's actually a lot in this chapter. There's type 1 and there's type 2. Type 2 has an infinity coming from the integrand. So there's a bit to do, but for this video, we're going to focus on these type 1 kind of integrals. Okay? And they are pretty much, they're going to look like this, like the one we just did. From a to infinity of f of x dx, but they might also look like from negative infinity to a of f of x dx, and they might also be infinity on both sides. So we'll talk about each of these cases in turn. We do them exactly the same way we just did our example, our motivating example. You write the infinity as a t. You evaluate the integral, and then you evaluate the limit. Same thing here. Now, by the way, for those of you who it's been a little while since you had Calc 1, or knowing how to do limits and everything isn't that like strong in your head, this is a great time to review all of that, because most of these limits will not be terribly hard, but sometimes you'll get one that's a little bit tricky, and we have to sort of know what we're supposed to do with those. Okay, so if it's a little rusty, this is a great time to go back and review your basic limit laws. And most importantly, though, what's going on with those limits as you're going to infinity, or at a vertical asymptote, or those kinds of things. So this is a great time to review. Now, this last one, you've got negative infinity and positive infinity. This is a tricky case, okay? Because you might think that you could do it from minus t to t, but it doesn't work that way. It doesn't work right. And I'll tell you why in a minute. You have to break it up. And you can break it up wherever you want. Commonly, people break it up at 0, but you can break it up at any a. And then you have to do these two separately. The reason is because if you just do it from minus t to t, it might be something that cancels out. Like, let me give you a really simple example. What if I look at my friend y equals x, right? Obviously, if I'm doing that and I'm asking what's the area under that, well, this is going to diverge, right? Because I've got this all going off to infinity. There's no way I'm going to get any area from that. But if I don't break it up and look at them separately, look what happens. If I do minus t to t of x dx, right? Then I've got x squared over 2 from minus t to t, and this is just this minus this. It's 0, okay? So if I were to think that this was going to give me the area under that curve, I'm telling you the area under that curve is 0. Well, it's because obviously I've got a function which is odd over an even interval, and it's going to be 0. But that's not really what I mean when I'm thinking about plus or minus infinity. I want to look at those separately, because if I just looked at this separately from 0 to t, then obviously it would be going to infinity, right? So, and if I looked at it from negative t to 0, it would be going to negative infinity. So it's like, it's fake that they cancel out, because what we really want to be saying is that this function, you're not getting anything nice here. The area under that thing is going to infinity. Okay, so this is an important point. It's important and sort of a tricky point why that is so. But whenever you've got the plus and minus infinity, you have to watch that this stupid stuff doesn't happen. You have to break it up. And then, by the way, when you have broken it up, for this to converge, both of these integrals have to converge. If one of them goes away, then you're done. The whole thing diverges. Even if the other one's good, doesn't matter. The whole thing diverges if one of them diverges. All right. So I'll make another video with some more examples.